Good morning, friends. Yesterday in the last lecture we discussed about the number systems. Right, now today we are going to continue with the same topic, and today's topic is real numbers and their decimal expansions. Right, real numbers. What do you mean by real numbers? Real numbers actually means the mixture of all the numbers starting from natural number, whole number, integers, rational numbers and irrational numbers. Right, now and the decimal expansions. In the last lecture we also discussed how this decimal expansion can be brought, right? So the decimal expansion actually comes when we divide two real numbers, or let us say integers, right? When we divide two integers or two real numbers, we get some decimal expansion, right? Suppose, let me take for example, if I am having an example of 7 upon 8. So if I divide 7 by 8, right? If I divide 7 by 8, what shall I get? I shall get some decimal expansion of division, right? That means this will be 0.70. So 8 into 8, that will become 64. Subtracting this, I shall get 6 again, right? If we put a 0 here, that will be 8 into 7, that is 56. That will give me 4. And if I put a 0 again, that is 8 into 5, 40, right, with a remainder 0. So finally we can write like 7 upon 8 in decimals, that is 0.875, right? So that means when I divide two real numbers, that means if I divide 7 by 8, I shall get a decimal expansion of this, that is 0.875, right? Now what does this suggest? This must come to a conclusion. You can say that this decimal expansion is a terminating one. Yes or no? Terminating. What do you mean by terminating? Terminating, that means it is ending. There is no further division after we get this 5. That means there is no further division after the third decimal point, right? What does this clearly indicates? That the decimal expansion we got it for 7 upon 8 is a terminating one, right? Now there may be some more examples like this, which comes to a conclusion that whether the decimal expansion of the numbers that we get is a terminating one, whether it is a non-terminating one or whatever, right? Let us discuss some of the examples here, and then we shall come to a conclusion that when we divide two real numbers, then at that time what is the decimal expansion of those real numbers, right? I am having three examples here. The first one is 10 by 3, the second one is 7 by 8, and the third one, that is 1 upon 7, right? These three examples will give me three different solutions. Suppose if I divide 10 by 3, that will give me 3 into 3 is 9, remainder 1. Again if I put a point here, that will become 10, that is 3 into 3, 9, again a 10, 3, 9, again a 10, and so on. That means what we can say, that 10 upon 3, that is equals to 3.33333 and so on. That means it is not going to end anywhere. Similarly, as we see in this 7 upon 8, that is 0.8 gives me 64 with a 6 as remainder. Again if I get it 0 here, that will be 8 into 7, 56 with a 4 remainder. Again if I put a 0 here, that will be 8 into 5, 40 with a 0 remainder. That means what can I say here? That 7 upon 8, that is equals to 0.875. Here we got it as 3.333. And the last one, that is 1 is to be divided by 7. So again if I put 0 point, that will become 10, 7 into 1, 7, 3, right? Again putting a 0 here, 7 into 4, 28 with 2 as remainder. Again putting a 0 here, that will be 7 into 2, 14 with a 6 remainder. Again putting a 0 here, that will be 7 into 8, 56. Again 4 as a remainder, putting a 0 here, that will give me 7 into 5, 35. Again 5 as a remainder, and if I put a 0 here, that will give me 7 into 7, 49 with a 1 remainder. Right, now you can see clearly friends that this is a remainder 1 here. If I put a 0, that will become 10, and see the number from where we did start here, that is again a 10. Right, that means if I continue the division here, then this set of number that is in the quotient, that will be repeated again. Right, this set of number that is 0.142857, that will be again repeated. That means here I will get 142857 and so on. Right, what does this clearly indicate? That means a block. Let me say this as a block of number. Which one? This 142857 as a block of 6 numbers that is repeating again and again. After 6 divisions, it is going to repeat itself again. Right, that means 1 upon 7. This can be written as 0.142857, 142857, and so on. Right. So let us now write this in the simplest form, that is equals to 3.3 bar. This cannot be written anything in the bar, and this can be written as 0.142857 bar. Right. Now friends, you will come to a question that, sir, what is this bar here? Bar, that means the number under that bar is repeating itself. Right, number under that bar is repeating itself. If I write here 3.3 bar, that means this 3 is repeating here. Right, 3.3 bar, that means this 3 is repeating here infinite times. Here 0.142857 bar, that means this block of 6 numbers 142857 is repeating itself infinite times. But see here, what is repeating? A block of number is repeating, and what is repeating here is only a single number is repeating. Is it clear? So what can you say about this? This is again a non-terminating number. Non-terminating, that means it is not ending anywhere, not ending up to infinite places. Right, that is known as a non-terminating number. Here see, this further division, as the remainder becomes 0, the further division is not possible, hence that is known as a terminating number, or let me write down here as terminating only, then we shall discuss later on about this terminating or terminating number. Right, and the last one again, that is a non-terminating number. Right, so what does this show? That when and when the remainder is not getting 0 anywhere, that means the number will be a non-terminating number, and when the remainder is getting 0 here, that means this becomes a terminating decimal number. Right, so coming to the conclusion from this one, that if the first point, if the remainder becomes 0, then, right, if the remainder becomes 0, then the decimal numbers or the decimal expansion is a terminating one, is a terminating decimal expansion. Right, and the second point is, if the remainder is not 0, then the decimal expansion then the decimal expansion is either a non-terminating repeating decimal expansion or non-terminating non-repeating decimal expansion. Right, so this concludes this one, that if the remainder becomes 0, then you will get a decimal expansion is or as a terminating decimal expansion when the remainder becomes 0. Now if the remainder is not 0, then the decimal expansion is either a non-terminating repeating one or a non-terminating non-repeating one, right? Now you might come with a word in the textbook, that is non-recurring or recurring. Non-recurring or recurring simply means non-repeating or repeating. Non-repeating, that means the number is not going to repeat anywhere after the decimal. That means if I get an expansion here, let me say for example 1.432105 like this, right? That means see, none of the numbers here are repeating. If none of the numbers are not repeating here, then that is known as a non-recurring or non-repeating. And if for this example 10 by 3 and for this example 1 upon 7, see, we are having this block of numbers and a single number is repeating here, that means we can say that this non-terminating decimal expansion is actually a non-terminating repeating or recurring decimal expansion, right? So friends, how to define this when you get any non-terminating repeating or terminating repeating, anything like that? So what the basic thing is, all the fractions, all the rational numbers present to us are mainly classified into these three groups only. That means if a rational number is of the p by q form, then that will be either terminating or that will be either non-terminating repeating or non-repeating decimal expansion. So whenever you come across a decimal expansion, you will come to know that the decimal expansions are broadly classified into these three categories only. Either they will be terminating decimal expansion, either they will be non-terminating repeating decimal expansion, or lastly they will be non-terminating non-repeating decimal expansion. Is it clear? So the next thing that we are going to learn from this is how to convert the decimal numbers to the rational numbers. We have already studied in these three examples that how to convert a rational number into a decimal number, right? Simply by dividing the rational number by dividing the numerator by the denominator, we get a decimal number, right? That in that way we can get a decimal expansion, right? Now in this topic we are going to study about how to convert, right? We are going to study about how to convert a decimal number into rational number, right? how to convert a decimal number to a rational number. I'm having one example here that show that 0.33, see the first one that we have taken, or you can also write it as 0.3 bar is a rational number. Show that this is a rational number. If I show that this is a rational number, that means this is actually the decimal expansion of a rational number. Yes or no? Now, how to show that this is a rational number is very easier, right? Don't complicate it. It is quite a very easy format to do it, but you need to understand, or you need to learn some steps how to perform this. First of all, let x equals to 0.3333 up to so on, right? Let x be equals to this much. Now the second step is very important one, right? You are going to multiply on both these sides. You are going to multiply with both these sides in the multiple of 10 raised to n. In the multiple of 10 raised to n. See, right? The second step here will be, I am writing down the step. The next step after performing this is multiply on both sides by a number which is a multiple of 10 raised to n. Note that friends, this 10 raised to n, this n can be any natural number, right, except 0, right? N can be any natural number, that means the natural numbers does not contain 0 here. So if I say except 0, then I must say that this must be any whole number except 0, right? 10 raised to n, that means 10 raised to 1, 10 raised to 2, 10 raised to 3, 10 raised to 4 or anything, but such that the decimal places in the given question and that in step number 2 remains same, right? Such that the numbers in the decimal places in the given question and that in step number 2 remains same, right? This is my step number 2. Let me write down step number 2. This is my step number 1. Is it clear, friends? So what we have done first is that let x equals to 0.3333, that is my first step. Then my second step here will be I shall multiply on both these sides by a number which is a multiple of 10 raised to n, such that the numbers in the decimal places in the given question and that in step number 2 remains same. Now if I want to make this decimal places, that means the point after the decimals, if I want to make them as same, then what shall I do here is I shall multiply on both the sides by 10. So now coming to this question again, multiplying by 10 on both sides of equation 1. This is my equation number 1, right? Multiplying on both sides by 10 of equation number 1. Therefore 10x equals to 3.333, right? See friends, note that what I have done here is I have made the decimal places same. That means the point after the decimals are equal in both the equations. That means in equation number 1 and equation number 2, this both the things are same, right? That is what I am going to understand or make you understand here in step number 2, right? That you need to multiply by such a number on both the sides of multiple of 10, which gives me the same decimal places after the point on both the equations. That means in the given question, and that we got in step number 2, right? Now simply eliminate, that means to subtract equation 1 from 2. We are going to subtract the first equation from the second equation, not the second from the first, mind well. That means 10x minus x equals to 3.333 minus 0.333 and so on, right? So what I get here is 10x minus x, 9x equals to 3, and hence x equals to 3 by 9. This implies x equals to 1 by 3, right? So coming to the conclusion, very important one, that this decimal number, this decimal expansion given to us here can be written in the rational form as 1 upon 3, right? This means that 0.33, therefore 0.3 bar is equals to 1 upon 3, right? You can check it out by performing the reverse division. If I divide 1 by 3, then I must get the decimal expansion as 0.3 bar or 0.33. Is it clear, friends? So in this way we can obtain the decimal expansion of, in this way we can obtain the rational number of a decimal expansion, right? Okay, let me say for example I am having the second one. Show that 1.2727 up to or 1.27 bar is a rational number, right? I need to show that this is a rational number. So we shall perform the same steps here, right? We shall perform the same steps here. Just a minute, friends. Okay, now we shall perform the same steps that we have already performed in this first question, right? Okay, let us try to solve this again. For this question I am having, let 1.272727, see, you can write it up to 2 or 3 decimal places also, that is equals to x, right? Or let x equals to this. So this is my first equation here, right? Let x equals to this, or 1.272727 or 1.27 bar is equals to x. Now as I said, I need to multiply on both the sides by a number which is a multiple of 10 raised to n such that the decimal places in the given question and that in step number 2 will remain same. See, in clear cut way I say that whatever the number of blocks or whatever the number is repeating, you need to multiply on both the sides by that much 10 raised to n. In clear statement that here see, 2 numbers are repeating, 272727, 2 numbers are repeating, right? So you will need to multiply by 10 raised to 2. What is 10 raised to 2? 100, right? 10 raised to 2 is 100. So we need to multiply on both the sides by 10 raised to 2. If I say that here 3 numbers are repeating, then we shall multiply by 10 raised to 3, that is 1000, right? If I say that 4 numbers are repeating, then I shall multiply by 10 raised to 4. So here multiply by 100 on sorry, both sides of equation 1. Therefore 127.2727 is equals to 100x, right? Therefore let me say this is equation number 2. Eliminate or subtract equation 1 from equation 2. So what we shall get is 100x minus x is equals to 127.2727 minus 1.2727 and so on, right? If you subtract this, you might come to a conclusion that the numbers after the decimal places 1.27 and 127.27 number after the decimal places are being cancelled or are being cut. Therefore 100 minus x, that is 99x, is equals to 126. Hence we get 126 upon 99. This is what the value of x is. You can further cut it out by 3, that will be 42. I think you can further cut out by 3 also again, and that will be 14. Therefore x equals to 14 upon 3, right? Yes or no? So x will be, sorry, my mistake, 14 upon 11. We are going to cut by 3. So you can say that 1 point, this means 1.27 bar is equals to 14 upon 11. Is it clear, friends? So in this way we can obtain the rational number of any decimal number, right? In this way we can obtain the rational number of any decimal expansion. Again, let me say, for example, I am having one more example here, is show that (3.142678) is a rational number. How can you show that this is a rational number, friends? In the same way that we have discussed here, but see here it is neither a terminating number, it is neither a non-terminating number. So how can we actually show that this is a rational number? We cannot say that this is again a rational number here, right? Because we are not having any of the references to continue. So we must directly come to a conclusion from this, that we cannot say that this is a rational number. But yes, if I say that this is one of the values of a rational number, then what? This is one of the values of a rational number. Then what can you say about this? 3.142678, right? So the rational number clearly comes from this one, is 22/7. See, this is the value of pi, right? If you divide this 22/7, then you will get this number, that is 3.142678. You can clearly go on dividing this, but we cannot find it out by these methods. Why? Because here we are not having any of the references. In these two examples we were having this as a non-terminating decimal expansions, but here it is a terminating decimal expansion. And how to convert this terminating decimal expansion to a rational number is not yet being given in the textbook. So right now we will keep it as it is, that 3.142678 is a rational number, which gives us the answer of 22/7, right? So let us keep it right now till here. We shall solve this in the next lecture or in the class itself, right? Coming to the fourth one, or let me say the third one itself, show that 0.235 or simply 0.235 bar. See, there is a bar on the 35 only, is a rational number. Again, I am having one more question, that is 0.235 to 3535 or 0.235 bar, right? Bar is on 35 only. So what is the first step? Let 0.235 be equals to x. My very first step, right? This is my first step. The next step being, if this is equals to x, then look for such a number such that we are going to get the numbers after the decimal places same. So friends, this step, equation number 1, this step will now be multiplied 2 times so that we can make them same, because see, there is this 2 extra. If we multiply it by 100, then also we are not going to get the same decimal number, because in the first equation we are having this 2 extra. So first of all, we need to make that 2 come out of the decimal number or come out after the point. So first multiply equation 1 by 10. Multiplying equation number 1 by 10, so, or by 10 on both sides. So what shall we get is 2.35 is equals to 10x, that is number 2. And now we shall multiply by 1000, that is 10 raised to 3, because once I multiply it by 1000, this point will be shifted 3 places to the right side, right? And hence we get that decimal number after the point as 3535. Now multiplying equation 1 by 1000 on both sides, so we get is 235.3535, that is equals to 1000x, right? And that is my equation number 3. Is it clear, friends? Now you can clearly notice what, that the numbers after the decimals is same 3535 in equation number 2 and equation number 3, not in equation 1 and 2, or neither in 1 and 3. So what the thing is, eliminate or subtract equation 2 from equation 3. We shall subtract equation number 2 from equation number 3. That will give me 1000x minus 10x equals to 235.3535 minus 2.3535 and so on, right? That is 235.3535 up to infinite minus 2.353535 up to infinite. So that the numbers after the decimal places 353535, that will be cancelled. Hence we get 990x equals to 233, and hence x equals to 233 upon 990. Is it clear, friends? So the rational number, that means 0.235 bar is equals to 233 upon 990. This is what it shows. Clear with this, everyone? Right? So that the rational number of 0.235 bar is 233 upon 990. Clear with this, everyone? Okay. See, friends, if you want to write it down, then there is a way, that means if you pause the video and take a screenshot of it, that will remain in your gallery, or you can simply pause the video and then write it down and then you can continue with the video again, right? So that is the best part when you are teaching on a video lecture, that you can pause it whenever you want it and then you can simply continue with the rest. Okay, let us solve one or two of the same kind and then we shall move further with a important conclusion. The fourth one, show that 0.6 bar is a rational number. This NO simply means rational number. Okay, 0.6 bar. So here let 0.6 bar, that is 0.666, is equals to x. So we have taken 0.666 as x, then multiply by 10 on both sides of equation 1. Right, multiply on both sides by 10 of, on both sides by 10 of equation 1. Therefore, we shall get 6.6666 is equals to 10x. Right, this is my equation number 2. Subtract equation number 1 from equation number 2. Right. Now, what we are going to do here is simply subtract them. 10x minus x is equals to 6.66 minus 0.666. That gives me 9x equals to 6 and hence x equals to 2 by 3. That simply means 0.6 bar is equals to 2 by 3. Right, that simply means 0.6 bar is equals to 2 by 3. Hence that is our required rational number. Is it clear, friends? Okay. Again, show that 0.47 bar. Right, it is only bar on the 7. 0.47 bar is a rational number. So again, let 0.47 bar is equals to 0.4777 is equals to x. So as we did in that third example, that previous one on the left, right, okay, here on the left side of the board or left side of me, that was of the same kind. So first of all we shall multiply it by 10 and then we shall multiply it by 100 so as to make the numbers after the decimal point same. So multiply equation 1 by 10 on both sides. So we get 4.777 is equals to 10x. Number 2, and multiply again 1 by 100 on both sides. So what we get is 47.777 is equals to 100x, that is number 3. Right, now simply subtract right? Simply what you need to do is subtract equation 2 from equation number 3. So we get is 47.777 minus, sorry, let me write down the right side first. 100x minus 10x is equals to 47.777 minus 4.777. So you can see that clearly the numbers after the decimal place or numbers after the decimal point is being cancelled. That will become 90x is equals to 47 minus 4, that is 43, and hence you can say that x is equals to 43 upon 90, right? Therefore 0.47 bar, that is 43 upon 90, that is the answer. Is it clear? Right? So for 0.47 bar is equals to 43 upon 90. Okay friends? Okay. Now I shall give you one of the sum in your self-study. .001 bar. It is very easy, right? If you come with a conclusion from this, then it is very easier one to solve it, right? Now once we solve all these 6 of the examples, you are going to solve this by yourself, friends. Okay, once we solve all these 6 of the examples, we are going to come to an important conclusion, right? That we are going to come to an important conclusion that this is very important to be remembered whenever you are having a decimal number or a rational number, that the decimal expansion of a rational number is either terminating or non-terminating recurring. That means whenever you are having a decimal number with a terminating decimal expansion or a non-terminating recurring decimal expansion, then and then that decimal expansion will show a rational number. Or we can say that any rational number will always give you either a terminating decimal number or a non-terminating recurring decimal number. The decimal expansion of a rational number is either terminating or non-terminating recurring, right? That means whenever you are having a rational number, that will always give you a terminating decimal expansion or a non-terminating recurring decimal expansion, right? When there is a rational number. And the second point is the decimal expansion of an irrational number is always a non-terminating and non-repeating or non-recurring, right? So friends, clearly understand this, that whenever you have a rational number. What do we have? A rational number here in this case, right? We are having a rational number, and the decimal expansion of this rational number will always be either terminating or either non-terminating recurring decimal expansion, right? If it is a rational number. If it is an irrational number, then at that time the decimal expansion will always be a non-terminating, non-recurring decimal expansion. Non-terminating, and at the same time it is non-recurring decimal expansion. So understand this clearly, friends, that this will always give you either of these two. Which one? If it is a rational number, then it will give you either terminating or non-terminating recurring decimal expansion, and if it is an irrational number, then it will always give you a non-terminating, non-recurring decimal expansion. Is it clear, friends? So in this way we can divide the decimal expansions of these two numbers, right? Whether it is a rational or whether it is an irrational number. Is it clear? Okay, so let me remove this, and coming to an important topic again from the part of a number line. Okay. Now, we are having the number lines, right? In the very first topic of this chapter, we discussed about the number lines. The number lines basically means a line on which we can show each and every number present to us in the universe, right? Where we can show some irrational numbers, where we can show some rational numbers, where we can show some integers, where we can show some real numbers, or we can show some whole numbers. All the numbers can be represented to us in the form of a number line. But what about when we are having a decimal number of 5 to 6 decimal places or more than that? At that time, if we want to clearly understand that where will this number lie, then we are going to use the successive magnification method, showing or locating a decimal number on the number line. Right? Suppose if we want to show, okay, we know that this is our number line. Which is, here it is minus infinite, here it is plus infinite with a 0 here it will be 1, 2, 3 and so on. Here it will be minus 1, minus 2, minus 3 and so on, right? Now if I want to make this understand, then what I am going to do is, we know that these are now the integers that we have, the positive integers on the right side, the negative integers on the left side. Suppose if I see that I want to show 0.5 here, then what I'm going to do is, I'm going to show it here as 0.5, and I know it that this will lie in between 0 and 1. But what if I want to show a number that is like 3.1434? Then where will I show? It will be obviously, if you say that it will be obviously between 3 and 4. But if I want to locate the perfect location of this, then what? Then I shall use the successive magnification method. This can be shown by successive magnification method, right? Successive magnification method, that means it is like magnifying the scale, right? If I am having an Android phone, then if I pinch the screen, right, if I pinch the screen, then what happens? It goes in, that means the screen is like coming out, that means the zoom in process is being done here. In the same way, we are going to zoom in to the scale and we are going to locate that perfect number here on the number line, right? So if, let us say for example, I am having this 3.1434 on the number line to be shown, right? What is the number given? 3.1434. I want to locate this on the number line. Then what I am going to do first of all is I am going to draw a number line which shows 3 and 4 only right now for us, right? So if I say that this is 0, here it is 3 and here it is 4, I shall draw somewhat bigger, or let me draw it like this only by our regular number line, so that you can come to know that how to take the scale. There is no need of taking the scale here, but you need the scale such that you can measure out the centimeters, right? You can measure out the centimeters between the two of them. This is my 0, 1, 2, 3, 4 and 5. So this is my number line. Now first of all, we shall look for the very first number, that is 3, and it is 3 point. So it will lie between 3 and 4. So what we are going to magnify? We are going to magnify this 3 and 4 here. So that will show us like this somewhat. Right, this is my 3 and this is my 4. Is it clear? Now what I am going to do here actually is I shall divide this 3 and 4 into 10 equal parts. So it will be easier for you to understand that if you measure 10 centimeter on the scale here, 10 centimeter each of 1 centimeter, and then you just note down the numbers, right? So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Right, that means this is 3.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that will be 4. Or you can simply say that this is my 4. Right, so that will be my 4. This is my 3.1, 3.2, 3.3 and so on up to 4. Now once I get this 3, then I shall go for the next number. First of all, what did we do? We located 3, that lies in between 3 and 4. Right, now the next thing we shall locate is 3.1. So that is 3.1 here. And the next point we are having is 3.14. This 3.14 will actually be in between 3.1 and 3.2. So again we shall magnify this now. What? This 3.1 and 3.2 will be magnified here. That means if this is 3.1, then I shall show 1, 2, 3, 4, 5, 6, 7, 8, 9 and this will be 3.2. So you can say that this is 3.2 and this is 3.1. Now I shall show 3.14. You are going to go point by point. So first of all, what did we do here? We located 3, then we located here 3, then we located here 3.1. Now we are going to locate it here 3.14, right? So this is 1, 2, 3 and 4. So this one is 3.14. Is it clear, friends? See, here it is 3.1, here it is 3.14. Now the next point that you are going to locate it here is 3.143. That will again lie in between 3.14 and 3.15. Right. Now again I am going to draw a line here that shows me the magnification of this 3.14. 1, 2, 3, 4, 5, 6, 7, 8, 9 and that is 3.15. right? So this will be my 3.14, this will be my 3.15, and I shall see now that is 3.143, right? So 3.143, that is 3.141, 142 and 143, and this will be my 3.144, right? Now again the last one, that is 3.1434. so again I shall magnify this both, that on the number line we are having this as 3.143 and dividing into 10, 2, 3, 5, 6, 7, 8, 9 and 10, so that is 144. And if I want to locate 1434, then where is 1431, 1432, 1433 and 1434. So this point is my 3.1434, right, with the magnification here as this, right? So friends, this is just for the sake of you to make understand that I have drawn here the number line by successive magnification method. Is it clear? So that is how, first of all, we shall locate the first decimal here, after that we shall locate the second decimal, after that we shall locate the third one, and finally we get the fourth one. Is it clear, friends? Okay, now I shall draw one more example for you, and then I shall give you one or two in the homework session. That means you can do it by yourself, right? Okay, one more example here is me that locate 5.37 bar on the number line up to 5 decimals, right, up to 5 decimal places. So for this, what we are going to do is, we are going to first of all draw the number line, as we were discussing about how to locate this 5.37 bar on the number line up to 5 decimal places. So here given number is 5.37 bar, but we need up to the 5 decimal places here. That gives me 5.3777, right? So we are going to take up to this decimal places only, because we just need up to the 5 decimal places. So that's it, up to 5.37777. Now we are going to locate this on the number line. So first of all, this is 5.3, right? So first what we shall discuss, or what we shall locate, is 5.3, that lies in between 5 and 6. So on the real number line, first of all I shall locate this 5 and 6. So that will be 4, 5, 6, 7 and so on, right? I shall take that much part of the number line only, that gives me 5 and 6. So in the next number line I shall locate, this is 5 and this is my 6. I shall now divide this into 10 equal parts. So as I said, what you are going to do first is, you are going to mark 10 points on the next number line. First mark the points, right? First don't write it down 5 and 6 here. What you are going to do, first mark 10 points at 1 centimeter each. 10 points at 1 centimeter each, that gives me 1, right? 2, 3, 4, 5, 6, 7, 8, 9 and 10. This is my 10 points, right? Now the first point will be 5.1, right? Because I am showing the numbers between 5 and 6. So let me say this is 5.1, 5.2, 5.3, 5.4, 5.5, 5.6, 5.7, 5.8, 5.9 and 6.0 or 6. You can simply write it as 6 also. Is it clear? Now the next thing we are going to locate here is 5.3, that lies in between 5 and 6. So that is 5.3. This is my 5.3. So I've got a number 5.3 here first of all, right? Now we shall go for the next decimal place, that is 5.37. That will lie in between 5.3 and 5.4. So I need the next place also, that is 5.4. Again I am going to draw a number line and I am going to mark 10 places, each of 1 centimeter. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. These are my 10 places. The first place would be referring to 5.3 and the last place would be referring to 5.4. Right? Sorry, not 5.3, this will be 5.31. You are going to take the next place. So 5.31, 5.32, 5.33, 5.34, 5.35, 36, 37, 38, 39 and 5.40, or you can simply write it as 5.4 also. Right? Now, what is the next place to be located? 5.37. So that is 1, 2, 3, 4, 5, 6 and 7. So this is my 5.37. Is it clear, friends? So this is how I got a location of 5.37. Now in the next we are having 5.377. that lies in between 5.37 and 5.38. So I am going to have this next point also, that is 5.38. Okay, so drawing another number line that gives me the numbers, again dividing this into 10 parts, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. The first number will be 5.371 and the last number will be 5.380. Is it clear, friends? Right, so that is how we can show 5.371 and 5.380. Now again I want to locate 5.377. So 371, 2, 3, 4, 5, 6 and 7. So that is my 5.377. Is it clear? I shall need the next point also, because for the next decimal I shall need 378. Right? Now we shall show 5.3777. This is 3 sevens, which lies in between 5.377 and 5.378. So again I am showing a number line here that will give me 5.3771. 2, 3, 4, 5, 6, 7, 8, 9 and 10. That is 5.378. Right? Is it clear, friends? So this will be 5.3771 and 5.378. This is the number 5.3777. Right, again for the last one, that is 5.37777, I shall need 5.3777 and 5.3778. right? Sorry, 778 only. So this is the last number, and again showing it on the number line, dividing this number line into 10, 2, 3, 4, 5, 6, 7, 8, 9 and 10. This will be 5.37771 and this will be 5.37778. Right? Sorry. Okay, 5.3778 and 5.3771 only. Okay, now I shall require the decimal, that is 1 2 3 4 5 6 and 7. So that is 5.37777, which is our required decimal number, right? So the required decimal number lies in between 5.3771 and 5.3778. Is it clear, friends? So in this way you can show the decimal number on the number line. Now we are having one or two of the examples that you are going to locate it on the number line in your homework. So locate 3.765 on the number line, and the second one locate 4.26 bar on the number line up to 4 decimal places. Is it clear, friends? So you are going to locate these two, that is 3.765 on the number line and 4.26 bar on the number line in your homework or in your self-study work. Is it clear? So that's it about how to locate a decimal number on the number line.